Hello! In section 4.4 we will talk about the second derivative and some of its applications. There's actually 4 applications that we will discuss. One is concavity, concave up or concave down. One is points of inflection, and we'll talk about what these terms mean in a minute. Then there is acceleration, we've already seen that. And finally, there's a test called the second derivative test, which is an alternative to the first derivative test we've talked about recently. It allows to determine whether an extreme value is a maximum or a minimum. First, let's talk about concavity. If we calculate the second derivative of a function and we find an interval on which the second derivative is positive, what it means is that the function is concave up. What is a concave up function? It's a function whose graph is curved like this. And if you imagine you're a bicycle riding on a road and you're viewing yourself from a satellite, you're actually advancing and turning left. So when a graph turns left, this is called concave up. If the second derivative is negative on a certain interval, then it is called concave down. And if you are on a bike, then it is turning right. Finally, a graph often goes up and down again, and there are places on graphs where the concavity changes. In this example here, it's concave up until approximately here, and at that point, for a very brief instant, you're going straight with your bicycle, and then you're turning right instead of left. So the point where the concavity changes, somewhere around here I would say, is called a point of inflection or an inflection point. So, inflection points and concavity are closely related. Notice that when we talk about inflection points, it's one point or several points, but it's in one specific value of x. Whereas when we talk about concavity, it's often on a certain interval. We say the function is concave up from here to there. So how are we going to find inflection points and concavity? Of course, we have to start by finding the second derivative. So this is a polynomial, so it's pretty straightforward. F prime of x is equal to x squared plus 4x minus 3, and then f double prime of x is 2x plus 4. Points of inflection are where the concavity changes from positive to negative or from negative to positive. So that happens when the second derivative is either 0, that's how you can go from negative to positive because you're going through 0, or from positive to negative because you're going through 0. There's also another option, and that would be that the second derivative would be undefined. So for example, you could have, if you think hard, you may come up with an example of a sharp turn where before the sharp turn the graph is concave up, and after the sharp turn the graph is concave down. It's not that easy to make a graph like that, but if you think about it, you may be able to. So here this is never undefined, so we are going to look for the value or values of x where f double prime of x is equal to 0, and we find that it is at x equals negative 2. Before we declare that it's a point of inflection at x equals negative 2 and the corresponding y value, finding it using this, we should double check that the concavity is really changing from negative to positive or from positive to negative. It's easy to do when it's a line. If it's not as easy to do, we will have to wait a little bit, and typically we will be using a number line. For concavity, we are definitely going to want to draw a number line, and on that number line we are going to show every place where f double prime is either 0 or undefined, because these are places where the concavity could change. In this first example, there is only one such value of x, it's x equals negative 2, so our number line is going to be splitting at x equals negative 2, and now we just need to pick a value, a sample a number below -2 and the sample number above -2 and see whether f double prime is negative or positive. For the number above -2, the easiest choice is to choose x equals 0. So if I plug in x equals 0 in f double prime, I see that I get f double prime of 0 equals +4, so it's a positive number. And then for a value like below -2, I can choose -20, whatever. It's so easy here. 2 times -20 is -40, plus 4, -36. So clearly it is a negative value. So f is concave down from -infinity to -2 because the second derivative is negative, and f is concave up from -2 to +infinity because the second derivative is positive. Now that we've verified that the concavity changes from negative to positive, we can confidently write that there is a point of inflection at x equals -2, y equals 4/3. So these were the first two applications of the second derivative, points of inflections and concavity. Here's an exercise where we get an acceleration. So a particle is moving along a horizontal line with position function s of t. T is bounded by 0 and 5, so it's a closed interval. We are asked to find the velocity and the acceleration of the particle, and then to describe the motion of the particle. So this is a general term. It might be more precisely expressed in a quiz or a test. Here it's going to be describing whether the particle is moving to the left or to the right, and whether the speed is increasing or decreasing. Once again, we have a polynomial, so finding the first derivative, s prime equals v, is easy, and finding the second derivative, s double prime equals v prime equals a, is also easy. In such an exercise, we need to make a number line with both a and v, and we'll see why when we talk about the speed. So looking at places where v is equal to 0, we can either factor this quadratic expression, or we can use the quadratic formula. In any case, we will find that t equals 1 and 11/3. From here I can think backward and determine that the factorization of v is v of t equals 6 times t minus 1 times t minus 11/3. So I would put t equals 1 and t equals 11/3 on my number line. I would be very careful to show that it stops at 0 and it stops at 5, because unlike what we've done in previous section, where I could just choose t equals 5,000 or 1,000, just a huge number, here I wouldn't be allowed to do that, because I have to pick a number within the given interval, and the interval is bounded by t equals 5 and t equals 0. Now, when is a of t equal to 0? That is when t equals 7/3. That's when you solve, you would find 28/12, and we've simplified that a little bit. So I will also add 7/3 where it belongs. It is between 1 and 11/3. And now I need to make my number line. Normally, if you don't have a polynomial, make sure that you also add on your number line any values where v or a are undefined. But when you have a polynomial, those are never undefined. So let's start with a. It's the easiest. When is that negative? When is that positive? It only has an interesting value at t equals 7/3. So we can pick any number before 7/3, and we know that both this and that will have the same sign, because a is not changing at 1. We only put this t equals 1 here because v was possibly changing. V was equal to 0 here, a is not. So maybe we can choose, we could choose t equals 1, but to avoid confusion, let's choose t equals 1/2. So we plug in a of 1/2, so it's equal to 6 minus 28. A is definitely negative here. It's also going to be negative here because t t equals 1 doesn't affect a. And then for values above 7 over 3, we can pick any one. Let's pick t equals 3. And if we plug in, we get 36 minus 28, so a is positive on the right of 7/3. What about the sign of v? So v is equal to 0 at t equals 1 and t equals 11 over 3. So this time it's the 7 over 3 that doesn't matter. This sign here is going to be equal to that sign there. This one is equal to this one, because 7 over 3 isn't changing anything about v. It's a value that we had only for a. So first let's find a number between 0 and 1. We can take 1/2, and this is a little bit more work to find that 6 times 1/2 squared minus 28 times 1/2 plus 22 is actually a positive number. So we put a plus. Then we need to pick any number between 1 and 11 over 3. So we could pick t equals 2. Sounds like a good choice. 6 times 2 squared minus 28 times 2 plus 22, and find out that this is negative. So we would have negative, negative, both with only one step. And eventually we can choose t equals 4 for the last interval. So 6 times 4 squared minus 28 times 4 plus 22. And if you do it, you will see that it gets a positive. So it's a positive value, so we can add the plus here. So, describing motion. Firstly, let's talk about the particle, whether it's moving left and right. This is only related to the sign of the velocity. So when the velocity is positive, like here, the particle is moving right. When the sign is negative, like in these two cases, the particle is moving left. Finally, in the end, the particle moves right again. So if my cursor was the particle, it would be moving right, and then it's moving left, and in the end it moves right again. So we can see, if we split the 4 intervals that we have, the particle is moving right, and then it's moving left between 0 and 1, and it continues to move left between... it's moving left from 1 to 7 over 3, and then it continues moving left from 7 over 3 to 11 over 3, and eventually it turns around again and starts moving right until t equals 5. What about the speed? We've talked about that previously. The speed is a bit more complicated to figure out whether it increases or not, but the key concepts are written here. If the velocity and acceleration have the same sign, so they both contribute to the same direction, the effect is that the speed increases. If the velocity and acceleration have opposite signs, that means they kind of nullify each other, they exhaust each other, and the speed decreases. So this is when it's useful to have both the signs of a and v together on the same number line. We can see here a is negative, v is positive. That means the speed is decreasing. This is what we wrote here. On the second interval, from 1 to 7 over 3, we compare the sign. We notice they are the same, so the speed increases. Then the speed decreases, and finally the speed increases. So how can I show that with my cursor? Again, I'm going to be moving here left and right. In the beginning, it's moving to the right because v is positive, but it's slowing down. Then it moves left and it goes faster and faster. Then it continues to move left, but it's slowing down. And finally, it starts moving right again, faster and faster. So these key concepts here are important to know. Velocity positive means the particle is moving right. Velocity negative means the particle is moving left. And then what I just read earlier. This could also be up and down. If it's positive, it goes up. If it's negative, it goes down. So this was the third out of 3 applications, and now we will talk about the second derivative test. Note, firstly, just as an introduction, that if f prime is 0, it means there's a horizontal tangent. It doesn't always mean that there is a minimum or a maximum. It's frequent, but not always the case. So here, on this function there's a horizontal tangent line at this point. However, it's neither a minimum nor a maximum. So what is the second derivative test? If you remember, we had a first derivative test. In order to use the first derivative test, we had to look for candidates for being minima or maxima, and then we could apply the first derivative test, which said that a candidate, a critical point, was a minimum if the first derivative changed from negative to positive. It was a maximum if the first derivative changed from positive to negative. That was the first derivative test. The second derivative test is another option. It replaces the first derivative test. It's a substitute. You can use one or the other, whichever one you prefer, whichever one is easiest in the specific situation you're dealing with. But you still, just like for the first derivative test, you still need to find the candidates. The second derivative test states that if f prime of c equals 0, so you have a value where there is a horizontal tangent line, then three things can happen. If f double prime is positive, that means the function is concave up, right? So the function would look like this. And you know there's a horizontal tangent there, so you know it has to be a minimum point. B, if the function is concave down, if you see that f double prime at that point is negative, then you know it's a maximum, because we are on a function that is concave down, so at the critical point, it has to be at the top of that curve because it's concave down. And finally, a little problem with the second derivative test. If you plug in a value of x or c and the second derivative says that it's equal to 0, then the test fails. You cannot declare whether whether that point is a maximum or a minimum, or if it's neither. It could be any of them. In fact, here are examples. You can try the second derivative test with y equals x cubed, and you will see that the test fails, and in reality we know from the graph of x cubed that it's neither a min nor a max. If you try the second derivative test with y equals x power 4, you will see that the test fails again, and we know from the graph that it's a minimum. If you try with y equals negative x to the 4, there's a negative sign here, then once again the test fails, but from the graph we can see it's actually a maximum. So everything can happen if f double prime of c is equal to 0. Don't make any assumptions. So let's try with this exercise here. Find the relative extrema for the function f of x equals negative 3x to the 5 plus 5x to the 3 using the second derivative test. So firstly, remember you have to find the candidates. So we calculate f prime of x and we set f prime of x equal to 0. That by simplifying a little bit, we can divide by 15, and then we can factorize x squared. Beware, do not divide by x squared from this step to that step, because if you divide by x squared, you're going to lose one of the solutions. X equals 0 is a solution to this equation. If you divide by x squared, you will suddenly not have x equals 0 as one of your solutions. So don't divide by x, instead factor out x. From here we see that all the possibilities are x equals 0, x equals 1, and x equals negative 1. Now we start the second derivative test. So here we could do the first derivative test instead, right? But we have the choice, and we decide, instead of looking whether the first derivative changes sign, I'm going to use the second derivative test. So I find the second derivative and I just plug the candidate values in. When x equals negative 1, the second derivative is positive, so I know it's a relative min. if I plug in x equals 0, I find f double prime of 0 equals 0. So the test fails. It could be either. If I plug in x equals 1, I get f double prime of 1 equals a negative number, negative 30, and therefore it's a relative max. When the test fails, you should not stop like here. If the question asks you determine whether there is a max or a min, you cannot just be satisfied by saying the test failed. You have to find an alternative solution. So if the test fails, you need to either fall back on the first derivative test, because that is not going to fail, or you're going to have to work with making a sketch or whatever is possible. In this example here in the note, there is actually neither a min nor a max at x equals 0. So that is the fourth of the 4 application of the second derivative. There is quite a bit of confusion between concavity, point of inflection, and the second derivative test. So I handed out a page like this that summarizes the 4 applications: concavity, inflection point, second derivative test, and acceleration. There is usually nobody confusing acceleration with any of the other 3 applications. However, 1 and 2 can be looked at together. Number 3, the second derivative test, should be really not confused with 1 and 2. So look at this A5 page that I handed out if you want to clearly understand the difference and not start mixing up and using concavity when you're doing the second derivative test, or using the second derivative test when you're just looking at concavity. Thank you.